Alright, in this video I'm going to introduce you to how to connect the free body diagrams we've drawn with the equation F equals ma that you've learned about before, and then see how to apply that to do a numerical analysis. And so let me just write this equation here. Net force equals mass times acceleration. Now, this tells us that if the force is on the object, if there is a net force, that it will be changing its motion, and that the amount of motion change will be dependent on the inertia of the object. All right, so in this situation, this is question number 11, and if you want to pause the video and read through that, that would be good. I'm going to draw a free body diagram of this. There is a person pulling at a 35-degree angle up like this. And they are pulling with 40 newtons of force. Let's label that force person on sled. Then we have a downward pull, which is the weight of the sled, earth acting on sled. Then there is an upward push from the ground on the sled. We could call that snow, but we get confused between subscripts. And then we have a backwards push, friction, ground on snow. Now, you might be interested in knowing why did I draw the normal force vector smaller than the weight vector, and the reason is because the combination of the upward pull of the string and the upward push of the normal force has to balance the downward pull of the earth, because this object is not changing its motion up and down, similar to the air puck experiment. And so what we're going to do then is take this picture and mathematize it. We're going to write out an equation which describes the forces, and we're going to do it along the x-axis, and we're going to do it along the y-axis. All right, so along the x-axis, we have, say in the positive direction, we have a pull from the string, but it's not the whole pull of the string, it's only the x component of the string. And in the negative direction, we have the friction force and the ground on the string. And together, those will tell us about the change in velocity of the object along the x-axis. Now, you might consider pausing and trying to write the y-axis equation yourself. This is what it looks like. The upward pull from the string on the sled, but again, only the upward part of that, minus the downward pull of the earth on the sled, plus the upward push from the ground on the sled. And again, that will be equal to the acceleration of the object vertically, which is also influenced by the mass. All right, now at this point, you could try to answer some of these other questions. For example, determine the normal force the ground exerts on the sled. All right, well, that's going to require that we determine these values, and we can do that by way of some trigonometry. There's our force person on sled at an angle of 35 degrees. So there is an x component of that pull and a y component of that pull. And you can use your trigonometry to figure that out. Right, so I've done the trigonometry there to figure it out. So now let's go ahead and put some numbers in here. This is 32.7. This was friction force, 30 newtons of friction force, and the sled has a mass of 5 kilograms. And so doing that will allow us to determine the acceleration of the sled along the x-axis. Now, what if we want to find the normal force the ground exerts on the sled? All right, well, in that case, the y force, the upward pull of the string, is that minus the weight of the object, which is going to be g times m, plus the normal force, ground on sled, and that should equal the mass times the acceleration in the y direction. All right, now